All right, so we're going to look at integrals and vector fields. And to do that, we're going to start with the idea of looking at what can happen if we want to integrate across an arc that moves through space. And so I guess the general idea would be, and we did this as we learned integration and we moved across a line, we found arc length. What we could want to do is, can we find arc length if we have a volume function or a density function? Can we find the mass of like a wire where we would have a linear density? Remember in one of my Calc 2 classes, someone saying, hey, what would really be a linear density, because everything has dimensions. But when you get something long enough, something long enough, its width can be so insignificant compared to its length that you can treat it as a line integral. So we have some function that's winding its way through 3 space, and we can talk about the vector that points to the line. So there can be some function vector, and we call this the position vector. So r as a function of t, that is a position vector that can represent some parameter that moves across this. And what we want to do is we want to look at what happens as we move from, let me put this in, I think, yellow. As we move from some t equals a to t equals b, and we partition this into segments. And so we have these little partitions coming about, and we can talk about get green here, the vector to the center of a partition. And this partition itself is some change in arc length for the kth element. And the position to that kth element is some xk, yk, zk. Right? And so we've created, little linear segments that move its way and twist and turn with our crazy little arcing worm here. And so, as we've done in many, many occasions, we say that we can sum up some n amount of these segments. We can make a sum from k equals 1 to n over this function of xk, yk, zk. Times our little differential, or our little delta in k. And, depending on how we partition this, we may actually get different values for s of n. If n is continuous, then in what we can do, let's make a little look-see over this. We'll say that RT then is going to be some g of t I hat plus some h of t j hat plus some ijk, some k of t k hat. And so this parameterization of pointing to these little vector segments as we parameterize out. And so we get these little chunks here being little compositions of what happens here. We can make some function that's composed out of the little partitions. And what we want to do is turn this into an integral. Now, we're going to assume that the norm of the partition approaches 0 as it goes off to infinity. This book's really good at using this notation early on, is that the size of our partition, the norm of the partition, goes to 0 as n goes off towards infinity. If you look back into chapter 5, when it introduces the integral, a lot of the problems will show this partition notation coming in and the norm of the partition approaching 0 as n goes off to infinity. And so even though it's twisted and curving, we're going to have it, create an infinite amount of items with an infinitely small size. And so we get a definition out of this that if f is defined on a curve C, given in parameters, given parametrically, by this position vector. So r of t equals to g of t I hat plus h of t j hat plus k of t k hat on the interval, or the parameter interval of a is less than or equal to t less than or equal to b. Then the line integral of f over the curve C. So we're going to get this integral over the curve of f of x, y, and z ds for our change in arc length is the limit as n goes to infinity of my sum of k equals 1 to n of this function pointing to the little points around my r and my delta and arc length. So again, we're playing this game, and this provides that the limit does exist. And so if the curve is smooth over this, so a smooth curve, if we go back to the definitions from Calc 1, means that we'll use a velocity vector, that the change in the position vector with the change in parameter t is continuous and never 0. All right. So that's if C is smooth. And the function is continuous on C. this limit will exist and this will happen. That means we can say that let me change my colors here as we put a relationship here, that the arc length given t will be the integral from 0 to t of the norm of v tau d tau. Right, we're doing a parameter switch here, and whoops, we'll make that should be a, not 0 to t, but a to t. And what we need to do then is ds will let be v of t dt. And so we can evaluate then in this parameter change here. We can say that we're looking for the value of the function over the curve will be the parameterization from a to b of my functions that make up my position vector. Integrated across the v vector and t. And so what we want to note here, let's see, I have this here, is if we look at ds dt and our Pythagorean relationship for where this is coming from, just so we note this. Whoops. My least favorite symbol is the square root symbol. We're looking for the change in the arc length with respect, or with the change to the x position with respect to the t parameter. The change with the y parameter and the z parameter with respect to the parameter. And so this Pythagorean relationship, well, ds then would be multiplying this to either side to get ds dt. And so what we want to do then is, how do we evaluate these line integrals? How do we follow ourselves on a twisty wire or a bead, right? It's like those toys that you see it in the doctor's office with the little beads that you flip to one side or another. That's what we have here. Is we have, you know, we're winding through space here, and we want to work over this. So to integrate, a continuous function over a curve C, we find a smooth parameterization of C. All right, so R of T, again, is going to be these functions that we need to find. Parameterized in T. between the endpoints that we're looking at, and then evaluate the integral. Oh, yep. Where each of the positional elements come from our parameters. If f is a constant value, if f equals 1, then this gives the length of C. So let's integrate, let's work on an example integral here. And we'll do this with a line example and work our way up to a different curving. Let's see here. All right, so we have our space here, and what we're going to do is in this space, we're going to integrate over a curve here. So let's see what is the curve we're going to want. So we're going to integrate the function f of x, y, and z equals x minus 3y squared plus z over the line segment, which is going to be our curve C, segment C, joining the origin to the point 1, 1, 1. Right, which is the diagonal of a unit cube, right? We have a unit cube placed on the origin, and so we're going to have this point come out. Let me see if I can get the point here. 1. Do this in yellow. 1. And up 1. And so the line segment that we're going to integrate over is that line segment. So there's the point 1, 1, 1. There's our origin, 0, 0, 0. And we're going to integrate over this line segment here. Some things to note, I guess this projected point downwards is 1, 1, 0, if we look at the downward projection. But we're going to integrate this function across that. Let me turn off my grid points now. And so what we want to do is we want to choose any parameterization, because anything we do here, any parameter that works will give the same answer. However we work our way across this, the integrals will create the same answer. And so what we want to do is, if I move 1 here, I move 1 up and 1 over. And so the book calls this the simplest parameterization for it, where we're going to make r of t equal t I hat plus t j hat plus t k hat. So as t moves, because this diagonal, every point on here has the same value for ijk, t will work its way from 0 to 1, and that puts our parameter t between 0 and 1. These have continuous first derivatives. So v of t is, well, the derivative of this is I hat plus j hat plus k hat. And that norm is 1 squared plus 1 squared plus 1 squared, or root 3. It's never 0. Right? This v of t never 0. Its norm never goes to 0. And so we can create our integral. Right? Remember, this is required not to go to 0, and the norm will always, of this parameterization, will always be root 3. So what we can do then is we can integrate over our curve C, our f of x, y, and z ds, which is equivalent to going from 0 to 1 in t of our function of t root 3 dt, which is integrating from 0 to 1 of, well, now we have to put t into our function x minus 3y squared plus z, so it's t minus 3t squared plus t times root 3 dt, or we'll bring the root 3 out. Oh, wait. There's 2t minus 3t squared dt, which is equal to t squared minus t cubed evaluated between 0 and 1, all times root 3, which is equivalent to 0. And so this function integrated across the line integral is equal to 0. We'll continue exploring line integrals in the next video.